Hello everyone, welcome. The underlying reason behind us being here today is that securing data across our connected devices is becoming increasingly challenging. Hacking already takes a toll on our privacy, finances, and our personal safety. The risks we face have been rising for years, and today they are reaching a critical point of inflection. The risks faced by both individuals and institutions continue to rise. All it takes is a quick search online to review step-by-step guides to hacking CCTV cameras or stall calls remotely. Each year seems to break records for cybercrime, with Samsung and Nvidia suffering severe data breaches in the last year. These risks increase the liability of manufacturers to secure our devices, who in turn are looking to the semiconductor industry to provide hardware-level protection that offers safe enrollment, authentication, and updates. It's a shift of responsibility that the market faces, which is now being reflected in government legislation. For example, Biden's national cybersecurity strategy, along with NIST's paper on hardware-enabled security, which was released this February, setting the bar even higher for manufacturers to secure their devices. So without further ado, let us introduce today's webinar topic, Enhancing Security in Embedded NVM Memory with PUF. In this presentation, we will share an introductory overview for this brand new PUF-embedded NVM solution and how it offers the best user data storage and protection experience in the market. Here's our outline. We are going to cover this webinar by answering the following three questions. The first question being, what is an NVM, or non-volatile memory? Where we will show you the basic concepts of an NVM and what characteristics a reliable and secure memory should have. Then we'll move on to the second question. What is a PUF? In this section, we'll demonstrate how to implement a chip-level physical unclonable function and reveal the features of an ideal PUF. After that, we'll show how to use this PUF-embedded NVM solution. This section combines the two technologies and reveals the potential applications for PUF-embedded NVM. We'll also show you why this solution is crucial to the current market and why we believe it will be implemented in every single internet-enabled device in the future. And finally, we'll close this webinar with a quick summary of what we have discussed. So let us begin by answering the first question. What is an NVM, or non-volatile memory? By definition, a non-volatile memory is a device that can store information even after its power is removed. People typically think of hard drives, floppy disks, or CDs on a computer, but we would like to dive a bit deeper than that. At integrated circuit or IC level, where tiny circuit devices called MOSFETs, along with much smaller capacitors or resistors that make up an IC chip, there is also the need for a hardware-level non-volatile memory solution. And this is where eMemory comes in, as we provide a wide variety of reliable NVM IPs that can fit perfectly inside an IC chip. Today, we'll focus on introducing NeoFuse, NeoPUF, and how this non-volatile one-time programmable memory can provide reliable data storage while adapting to various technology processes. What you see here is the fundamental memory unit of the NeoFuse OTP. You may find this cell structure remarkably familiar if you have some basic knowledge about MOSFETs. It is because the cell structure of a NeoFuse OTP cell is based on the core N-type MOSFET, one of the most standardized devices that can be found in any existing technology. So how do we turn an average NMOS into an OTP cell? Well, the key idea is how we apply the voltages. For NeoFuse programming, we apply high voltage on the gate terminal and ground voltage at either end of source or drain terminal. This voltage difference will induce a quantum tunneling path for electrons to tunnel through from the gate terminal and be picked up at the source or drain terminal. This path can be preserved in the oxide layer with sufficient voltage and stress time, and even when the power is removed. Once the memory unit is programmed, we can apply a read process to judge the state of the memory unit. For reading a NeoFuse memory unit, we would apply a read voltage to the gate terminal and ground voltage to either source or drain terminal. If the memory unit has been programmed, the current will flow from the gate terminal down through the quantum tunneling path and then be collected at the source or drain region. With that current detected, we will define this as digital 0. On the other hand, if the memory unit has not been programmed, there will be no quantum tunneling path inside the oxide region. Therefore, no current will be collected at the source or drain terminal, and we will define this state as digital 1. In terms of data preservation ability, using quantum tunneling path inside the oxide layer has been tested and verified to prove it can endure various environmental conditions, such as high temperature and radiation. Furthermore, the program path is guaranteed to last for more than a decade inside the oxide layer, showing excellent longevity in its data storage capability. Last but not least, the NeoFuse memory unit concept can also be adopted using FinFET devices, which are commonly used in advanced technology nodes to replace planar MOSFETs. That is why NeoFuse can provide reliable non-volatile memory storage across various technology platforms. Another upside of using quantum tunneling as a programming method is that the tunneling path is not observable. If you take an eFuse memory cell as an example, the two sides of the eFuse are connected at initial state. After program operation, the eFuse breaks and the rupture spot is easily observable under TEM or SEM inspection. With NeoFuse, even though the situation is the same where the rightmost cell is programmed, however, we cannot identify any difference between the programmed and the non-programmed states. And this is what we call the intrinsic data protection. With this secure feature, people can store their key information inside our NeoFuse IP without worrying about the possibility of any data being leaked by visual means. This security feature and great data storage ability are desired in various fields, from display driver to PMIC, camera, automotive, or even radio frequency ID. For any IC requiring safe data storage after power off, NeoFuse can fulfill that need with intrinsic data protection and additional features that can add to further improve data security. So the NeoFuse OTP has this intrinsic security feature. But how about its performance and data storage ability? Well, taking the recently qualified 5nm OTP as an example, our OTP IP has a wide voltage operation range, allowing our OTP IP to adapt to a wide range of potential products. As for its programming performance, we can see that we have a wide cell current difference between the programmed and the non-programmed states. This wide current window allows data to be stored perfectly under various environments without the possibility of misreading the stored data, providing excellent yield and reliability. Today, world-leading semiconductor foundries continue to explore the possibilities for shrinking electronic devices, pushing the advancement of technology nodes, which in turn adds greater functionality onto a single chip at a reduced size. NeoFuse has been following this trend of rapid technology advancement, providing reliable and safe NVM data storage, from mature technology nodes such as 0.13 micrometers down to one of the most advanced technology nodes, the 5nm technology. Since the memory cell unit is based on the core NMOS, NeoFuse is used in various processes ranging from High-V to CIS. Also, with more and more and the current trend of technology advancement, we expect to see our roadmap rapidly extend and expand. To sum up, our reliable and safe non-volatile memory, NeoFuse, contains the following commonly desired features by the market. Firstly, using the simple cell structure without the need of any extra process or masks result in high manufacturing yield and fast implementation speeds. Intrinsic data protection from programmed quantum tunneling paths can also secure data storage and reliability in harsh environments. At the same time, additional security features can be implemented in the OTP IP to provide best-in-class secure data storage. Lastly, the NeoFuse OTP provides a wide power supply range, low power consumption, and high performance. These features prove that NeoFuse is one of the most reliable non-volatile memory IPs in the current market. Now with NVM explained, we can now move on to the next question. What is a PUF? PUF stands for physically unclonable functions, which are used in hardware security primarily for chip identification and authentication. They utilize natural cellular level variations inherent in silicon to create an unclonable, unique device response to a given input. For example, NeoPUF's quantum tunneling PUF utilizes differences in oxide qualities, which comes from random microscopic variations between transistors. As such, they can be exploited to create a genuinely unique cryptographic key inside each chip at the hardware level. We call this chip fingerprint. It is similar to a human fingerprint as it is not predefined by any means, but generated randomly from its inherent biometrics. Now it is estimated that the collision probability, or meeting someone that has the exact same fingerprint as yours, is 1 out of 2 to the power of 66, which is practically impossible. But if we can implement a digital fingerprint, we could have an infinite number of unique IDs as long as the bit length is not limited. So having a random and unique fingerprint generated by the intrinsic property of a single electronic device is very feasible for future products. Now, some of you may ask, why does my phone or computer need a fingerprint of its own? Some may even argue, why not just give out these identities by marking every device sequentially? Well, the problem with sequential ID is that it is very predictable. This will pose a significant threat from hackers, as they may be able to exploit the weakness by masking themselves as one of the devices in the network. So to ensure that a hacker cannot predict an ID and use it to mask an adversarial attack on a system, we must use PUF to generate inborn device IDs that are random and unique. So how do we generate a device ID without programming any information into the device? Well, first we have our PUF bit cell shown in schematic format. In its initial state, the PUF cells appear almost identical to each other with minimum gate current. Then, with a uniform high voltage applied to both gates, either the cell on the left or the one on the right will form a quantum tunneling path in its oxide layer as it has a weaker oxide property compared to the other one. We define this process as enrollment. And when the tunneling path is formed, the high voltage stress on the remaining gate is relieved as a strong current flows from the other gate terminal to the data line. This is the self-inhibit property for the PUF cell that ensures a 50% chance for the right side being enrolled and a 50% chance for the other side being registered. After removing the gate voltage, we can apply a smaller voltage to one side of the cell pair to extract the data. If the cell on the right is enrolled, we identify this as data 0, and if the cell on the left is enrolled, we identify this as data 1. We call this the extraction process. After extracting the PUF data from the array of PUF cells, we will have a device unique ID generated from the intrinsic random characteristics of PUF cells that is for that specific electronic device. So here we demonstrate the actual measurements of the NeoPUF array under various technology nodes. The first we see from this is that there is no performance deviation regardless of the technology nodes. Then we can see that the ID generated from NeoPUF has an inter ID of around 0.5, which translates to perfect uniqueness. Now some may ask why 0.5 or 50% is the perfect uniqueness. Unlike humans, we may have a different response to a single trait. In the digital world, the ID is a string of zeros and ones. If today an ID is composed of 5 bits, and I tell you the other ID is 100% different from it, you would immediately get the other ID by simply flipping the zeros and ones. But if I tell you that the other ID is only 50% different from the known ID, we will then have to calculate all of the possibilities and perform trial and error to get the correct ID. This is why 50% is the best uniqueness trait for a digital PUF. Then we move on to the intra-ID characteristics of the PUF code. The intra-ID is measured by the number of different bits when the ID is read out repeatedly under different conditions. And as shown, NeoPUF has the perfect intra-ID characteristics, so the user need not to worry if the PUF ID suddenly changes one day. But there are more methods that can help us determine if a PUF is actually unique or secure enough. So, examining if a PUF code is random and unique enough to be unclonable is essential. If this random ID is not random or unique enough, a skilled hacker can still easily predict the next ID with extensive calculation and trial and error. So the randomness of the ID is a crucial factor. We have summarized the table to identify the qualities of an ideal PUF. We first analyze the randomness of the ID. This is achieved when the Hamming weight is 50%, meaning every bit has a 50% chance of being 0 or 1 to pass our first criteria for randomness. We will then look at its Hamming distance by comparing its ID to another ID generated using the same method. The ID is considered unique enough if the Hamming distance is 50%. After that, we'll check the ID's bit error rate by reading out the ID repeatedly. For an ideal PUF, the ID should stay consistent with every readout, so the bit error rate should be 0. Then we have the issue of helper data. Some PUF designs require helper data to reach the quality of an ideal PUF, but an ideal itself does not require such implementation. Moving on, we have bit length as an evaluation criteria. An ideal PUF should retain its randomness and uniqueness under long bit length. With this property, we'll be able to assign a PUF ID to every electronic product in the future without worrying if there will be any PUF ID collision. Since it is an unclonable ID, the ID should not be traceable under any condition, and its manufacturability should be 100% with no yield loss. Lastly, this PUF ID should not be affected by radiation of any kind. After listing out all of the required traits, we can put NeoPUF to the test. And as shown, NeoPUF's characteristics fit perfectly with the attributes of an ideal PUF. Thus, we can believe NeoPUF will export random device IDs that is unique between every electronic device. So what are the main applications for PUF? So the primary application for PUF is identifying devices, which we have discussed earlier. However, PUF can also be used in conjunction with dynamic entropy such as ring oscillator to generate more random numbers, which then can be used for communication or any other identification purposes. Lastly, the PUF code can also be used for data address scrambling, which I'll touch on that later in this webinar. As a quick summary for PUF, PUF is a unique ID generated by device's physical characteristics. This unique and random ID must be stable upon every readout while being random and unique enough to provide its unclonable and unpredictable future for device verification and authentication. NeoPUF is a unique identification generator that the market requires to provide device authentication to improve device authentication and verification. It can produce perfectly random and unique IDs per device while storing this data under harsh environmental conditions. It is also noteworthy that NeoPUF inherits the characteristics of NeoFuse. Thus, NeoPUF also demonstrates high reliability, high yield, low power, and high performance for device unique ID generation. Now with NVM and PUF explained, we arrive at the final question. How can we make use of this PUF-embedded NVM solution? To answer this question, we must first understand the need for this solution. With the age of IoT upon us, it feels inevitable that some electronic devices will eventually become internet-enabled. But how can you be sure that every device connecting to the network is legitimate and has not been tampered with? To prevent our privacy and finances from being hacked, we must take good care of our key information. And we're not talking about keys to unlocking doors. Instead, we are discussing digital keys for identification, authentication, encryption, and communication. These keys must be generated from a physical unclonable function for an optimal security configuration. And once generated, the key must be stored securely in non-volatile memory. In that case, we see the urgent need for a PUF-embedded non-volatile memory in the current market. Let's take a look at a real-world practical application. Artificial intelligence is rarely out of the news, discussing how it will be integral to the future of technology, yet it remains vulnerable to an adversarial attack. For example, using a compromised camera or speaker to undergo a poisoning attack. The hacker could corrupt the learning model's dataset through data injection, resulting in unwanted training results or potential failure. Therefore, the integrity of an AI model must be protected through secure boot and authentication for each connected module. And each module must also have a set of authentication keys to be stored in the board manager, which controls the secure boot process. To answer this need for secure boot process, we will need a device that can identify itself from others with a unique PUF code while storing this key information in a non-volatile memory, thus calling for a need for PUF-embedded NVMs. The main advantage of embedding NeoPUF is the device-specific random number the PUF brings. This random number can be used for key generation and to scramble physical storage data in the NVM section. On the left, we can see that if there is no PUF embedded, the NVM can only have a uniform data storage pattern amongst the producers in the same product generation. Without the help of PUF, a hacker can study the data pattern in one specific product. Then, once the scramble pattern is known, they can apply this knowledge about the scramble pattern to every product in the line and easily retrieve any secret data stored. But with PUF embedded NVM or secure OTP, the data storage pattern is device-specific. Suppose the hacker gets hold of one of the products and eventually discovers the scrambling pattern after numerous days of trial and error. In that case, this knowledge cannot be applied as the scrambling pattern between every device is unique. Therefore, in our secure OTP, PUF codes can not only be used to generate device-specific IDs, but their uniqueness and randomness can also be used to further protect your data from external threats. Let's take a closer look at the secure OTP. We can see that it has NeoPUF embedded in the NeoFuse architecture, demonstrated in the array region of the IP block diagram. The PUF code from NeoPUF cells can be used to generate device-specific ID or digital keys while also providing reference for data address scrambling. NeoFuse cells in this region can be used to store generated digital key data as well as other important information with intrinsic data protection and high reliability. The circuit blocks surrounding the cell array are high voltage charge pump used for pumping program voltage into the cell array. One-line decode, a circuit that can decode user-specified address into a specific location inside the array. At the bottom, we have ring oscillator entropy, a dynamic entropy source used in conjunction with the PUF code generated by NeoPUF to create device-specific keys for various purposes such as encryption, authentication, and verification. On the top left side, we have control circuit for controlling various circuit blocks, and above that we have bitline direction decoder and sense amplifier used to identify zeros and ones stored in the array. On the leftmost side of the secure OTP, we have additional secure features, a block containing our most advanced anti-tampering designs to further secure your private data. With these circuits, they form the basic structure of the eMemory secure OTP. The customer needs to provide some additional anti-tampering protection as well as secure controller, APP interfacing, and most importantly TRNG, user ID, and OTP encryption to take full advantage of the secure OTP. There's more. The secure OTP itself also comes with a set of security features covering various attacks that can be done on an IC chip. First of all, we have secure-oriented IP layout design when realizing the secure OTP. Since IC probing attack is only efficient when probing a certain critical signal lines, we only allow critical signals routings using lower metal layers and power routing using upper metal layers. This will increase the cost and difficulty of the attack as chip delayering is required, and for attackers to reach the critical signals, they will need to eliminate the power routings, which will in turn disable the chip. Second of all, we have hidden and obfuscated data interface. This feature is also used to increase the difficulty of probing attacks or focused ionic beam attacks. With pinout at metal 1 and metal 2, it will be very difficult for the attacker to reach the interface in the first place. And with fake I/O pins embedded, It would also increase the difficulty for probing attacks, as hackers would need to figure out which pin is the real pin. Last but not least, we have metal shielding. Since our IP does not require all of the metal layers to complete our signal routing, we can reserve one or more layers to implement a metal shield. This feature is used to prevent critical signal being leaked by electromagnetic waves, or increase the difficulty for side-channel attacks. We would also recommend our customer to add additional metal shielding or have signal routing going above our IP for additional protection. To increase the ability of data protection, there is even more protective features that we can offer. And all of these protective features are certified by third-party security evaluations, proven to be effective in protecting user key information. So to answer the need for secure boot, as well as better and safer digital key generation and storage, Secure OTP, a PUF-embedded NVM solution, is introduced. The Secure OTP comprises NeoPUF for device unique key generating and NeoFuse for reliable secure OTP storage. This solution offers intrinsic high security storage, as NeoFuse storage cannot be visualized externally. In the meantime, the Secure OTP also offers a unique fingerprint ID for every device, which can be used to increase hardware security, such as device unique data address scrambling. On top of that, Secure OTP also features a list of protective features that can protect secret data from various attacks. So lastly, our Secure OTP structure is approved by third-party security, providing effective upgrades that will further create a safe and secure digital ecosystem. Let's summarize the key ideas discussed today. The first being the definition of non-volatile memory. A non-volatile memory should have a high storage reliability even under the harshest environment and power off. NeoFuse fits in as it provides outstanding data reliability, high protection yield, and most importantly, the intrinsic data protection feature to hide stored data from hackers. The second item is the definition of a PUF, as providing every device with a unique inborn ID that never leaves the chip. It decentralizes the management of encryption keys and removes the threat vectors. PUF-generated IDs utilize the silicon's random physical attributes for device authentication. NeoPUF is a qualified and widely available PUF solution and demonstrates characteristics on par with an ideal PUF. Secure boot is the foundation for a more secure digital ecosystem where every device is verified with its own inborn ID. This will prevent unwanted imposters from being placed inside the network. Thus, we will need a PUF-embedded NVM solution to create a unique device ID and store key information with high data reliability. Secure OTP is a PUF-embedded NVM solution that can answer the need for secure boot in today's market. The Secure OTP offers a unique ID and reliable data storage and features random data scrambling that is unique between every device, while also featuring a list of protective functions that can further secure your data against hackers. And last but not least, the Secure OTP structure is a verified secure structure that can best protect your data. So upgrade your data storage security by giving your device a unique identity of its own with Secure OTP. This concludes today's webinar. Thank you all for joining.